Hi, we ended our last lecture by introducing isotopes, and we're going to begin with just a little review exercise to understand isotope notation and the information that we have from it. Now, this example, we're going to look at three isotopes, and we're going to answer some questions. We're going to name the element. We're going to list how many protons, how many electrons, and how many neutrons are within this atom of this particular isotope of this element. So C, that's carbon. And the first question we're going to answer is how many protons? So when we look at isotope notation, what we want to remember is the smaller number, and we'll underline it here, the 6, is the atomic number. The atomic number is the number of protons or the unique feature of that particular element. Every atom of carbon, regardless of what type of isotope, has 6 protons in it. How many electrons? Atoms are neutral. We're going to introduce ions in a little while in this lecture, but atoms themselves are neutral. They have to have the same number of protons and electrons to retain this state of electroneutrality. How do we figure out the number of neutrons? The number of neutrons can be derived from the mass number minus the atomic number. In this case, the mass number is 12. The atomic number, which is the number of protons, is 6. 12 minus 6, well, in this case, we end up with 6 neutrons for this particular isotope. Let's try another example here. Fe. Now, Fe is one of our transition metals. It's not one of the ones you need to memorize, but you should be able to use a periodic table and find that Fe is iron. The number of protons is the smaller number listed here. That's the atomic number, 26. Iron in its atomic form is neutral. It needs to have the same number of electrons as protons, which is 26. The number of neutrons is the mass number, which is the larger number, minus the atomic number. In this case, this would be 29. Okay, so we'll keep this one here in case people are keeping track. The last example, K, you should know this, K is potassium. The number of protons is the smaller number in the lower left-hand corner. And since it's a neutral atom, the number of electrons have to be equivalent. And the number of neutrons will be the mass number minus the atomic number. And for this particular isotope, we have 20 neutrons. So somebody did ask a question, are the number of protons and neutrons always going to be the same? No, as we just showed in this example right here, there are isotopes that do have different numbers of protons and different numbers of neutrons when we consider an atom. What's always going to be the same for a neutral atom is the number of protons, which are the positively charged particles, are going to be equivalent to the number of negatively charged particles, the electron. And that's important here as we demonstrate throughout this lecture when we start to discuss ions. Another example of how we can write our isotope notation is in some cases, we're simply given the symbol for the element and the mass number. Now, if we look at this example right here, we would go to the periodic table and we would see that this is magnesium. Now, notice in the shorthand notation, they don't give you the atomic number. They expect you to go to the periodic table, look up the atomic number, and in this case, the atomic number for magnesium on the periodic table is 12. You would see magnesium, you would see 12. and that would be the number of protons in its nucleus. Shorthand notation expects you to be able to do that step. This is a neutral atom, 12 electrons, and the number of neutrons, once again, in this case, it is equal to the number of protons. So that's an example of a shorthand notation. There's one other shorthand notation that you should recognize. Sometimes they give you the name, with a hyphen and a number. The number is the mass number. If we look at bromine 79, this tells us that this is an isotope of bromine that has a mass number of 79. The number of protons we would find from the periodic table. If we look up bromine, we would see that there are 35 protons, 35 electrons, and the number of neutrons is 79 minus 35, which is equal to 34. Oh, 44, my bad. Everybody good? Let's answer just a simple question. How many neutrons in chlorine 35? Well, if we look at the periodic table, we would see that chlorine has 17 protons. Therefore, chlorine has 17 electrons. The number of neutrons can be determined by taking the mass number minus the atomic number. Conceptual question. Again, these are the types of questions you might see on an exam or on your homework. Let's choose all the statements that are correct. Isotopes of the same element have our choices. Have different, we'll say different atomic numbers, mass numbers, protons, number of protons, number of neutrons. So let's think about this question. Isotopes of the same element. So these are going to be atoms that are derived from the same element. What do we know about atoms of the same element? Well, first of all, they're going to have the same number of protons. So we could say that this letter C, do they have different numbers of protons? No. They're derived from the same element. So this letter C cannot be true. They're going to have the same number of protons. And when we have the same number of protons, what that indicates to us that since these are atoms derived from the same element, they have the same atomic number. What's going to be different for isotopes of the same element is that they have different numbers of neutrons, and therefore they have different mass numbers. So that's an identifying feature of an isotope that you should recognize. Finally, I made some comments about isotopes and how they're used in research. Now, what's important about isotopes is that the chemical reactivity of an isotope will be the same for isotopes of the same element. Uh, and that's because most chemical reactivity involves electrons and protons, not neutrons. And therefore, the use of isotopes are really important in research. For instance, I have a few isotopes listed here. Iodine 131 is used for medical diagnosis of thyroid disorders. Carbon 14, it's used for radiocarbon dating. Uh, if you're into synthetic chemistry, if you go into organic chemistry, sometimes they use isotopic labeling to understand about mechanisms and how chemical reactions proceed. So what's important about isotopes is that they have different nuclear properties. Some of them are radioactive, not all of them, and some of them that are radioactive might be dangerous to us. So just a brief review. Atoms are neutral, therefore they have to have the same number of protons as the same number of electrons to balance out the charge and maintain a state of neutrality. Electrons are really important for chemical reactivity. And one type of reaction that we're going to study a little bit later in chapter 8 are called oxidation and reduction reactions. And these are reactions involving the exchange of the electron. And oftentimes, these types of reactions result in charged particles that we call ions. And what we're going to learn about when we get into our section in chapter 3 on the periodic table, we're going to learn how we can predict the possible charge that an atom may attain based upon its position in the periodic table. But for now, we do want to understand that ions form due to an imbalance between the number of protons and the number of electrons. And this is due to either an atom gaining or losing electrons. They have the same number of protons, however, the electrons may change. The first type of particle that we're going to look at is going to be the particle that forms due to the loss of electrons. So we're going to look at what we call cations. Cations, okay. Cations. And I like to underline the T. The T is important. I like to look at the T because that tells me it's positive. That's how I remembered them when I was in undergrad. There's our cations, positive. Cations. Cations form. These form due to loss of electrons. So when an atom loses electrons, there might be a loss of 1 electron, 2 electrons, so forth. We end up with a particle that now has an unequal distribution of positive charge and negative charge. These particles have more protons than electrons, and they end up being overall positively charged. Let's look at an example of an atom that we're going to, again, learn more about position in the periodic table and how we can make these predictions. For today, I'm just going to fill you in on a few that we know about. Let's look at beryllium, Be. If we look at the periodic table, we would see that beryllium, Be, has 4 protons. It has an atomic number 4. And therefore, beryllium is a neutral atom. It has 4 electrons. Now, beryllium is an atom that can undergo a loss of electrons. Beryllium might lose 2 electrons. Okay, we end up with a particle, the beryllium cation. Cations are positively charged particles. Let's look at the subatomic structure in terms of the number of protons and electrons alone. Well, what happens? It's still a beryllium. It's still beryllium. It's derived from the beryllium atom. And the number of protons are still 4. 4 units of positive charge. It's lost 2 electrons. So let's just do a little math. We have 4 units of positive charge, 2 units of negative charge. We have an excess of 2 units of positive charge, and we end up with a particle known as the beryllium cation. And we put a positive 2 in the upper right-hand corner to represent that this particle is charged by a factor of positive 2. And it's called the beryllium cation. 4 protons, 2 electrons. As I said, right now, it might seem like, how did you know that? Well, we're going to learn rules based upon the use of the periodic table and how we can make predictions of the types of ions we expect to form. A little bit later, I think chapter 3 is when we get into that. So, well, if we have particles that form due to loss of electrons, we also have particles that form negative charge due to gain of electrons. And these particles are called anions. Anions. And I'm going to put a parentheses around the end. And this is how I remember. Big N in the middle, it's negatively charged. Anions. Anions are formed, these are formed from the gain of additional electrons. Let's look at one particular atom. Again, we're going to learn why this is true. We'll learn how we can make predictions. Learning why is pretty detail oriented. You might have to take a more advanced class. Let's look at chlorine. Chlorine. Chlorine has an atomic number of 17. Therefore, the atom chlorine has 17 protons, which are positively charged particles, and it has 17 electrons, which are our negatively charged particles. And we have to have an equal number to have the neutral chlorine atom. Again, chlorine is a particular atom that actually can gain electrons. Chlorine can gain 1 electron, and now there's going to be an unequal distribution of positive and negative charge. We're going to have 1 more electron in comparison to the number of protons. And we're going to end up with what we call, and the name for this is the chloride anion. So this is important. Let's do an account. It's derived from chlorine, so there are still 17 units of positive charge, 17 protons in its nucleus. But now it's gained 1 additional electron. Notice there's an unequal distribution. We have 1 additional unit of negative charge, and that provides us with a -1. Now, normally we don't write the 1 when we write the negative if it's only one unit. We assume there's a 1 there. Same thing would happen for if we only have 1 unit of positive charge. When there's a 1, we don't have to write it. If you want, I'm not going to have a heart attack. I'm not going to die over it. My lab mastering might have some issues. So I'm just letting you know for right now, you don't need to write a 1 there. So this is an example of what we call an anion. It's a particle that's formed from an atom that gains an electron. And again, we're going to learn more about these and how we can make predictions based upon where these atoms are located in the periodic table. So let's just review a little bit about where we're at right now. And let's answer a couple of questions that I have on today's PowerPoint, reviewing some topics. So let's look at this question. 2 review questions. The first question deals with an element known as americinium. Americium. It's one of those ones I don't really use a lot. So americium 241. It's an isotope. And it's used in smoke detectors. We want to list the number of protons, the number of neutrons, and the number of electrons within the atom of this particular isotope. We would turn to the periodic table and we would look for the elemental symbol Am. When we look up Am, we can look in our textbook, we can look on a periodic table. We see that it has a 95 on it. Now 95, remember, is the atomic number. The atomic number is the number of protons. Whoops, 95. 95 protons. It's not an ion, it's an atom. It's an isotope of this element. So there are an equal number of electrons. Now the number of neutrons, well, that's found by taking 241 minus 95. That's 146. And that's the subatomic particles that are within that particular isotope. Let's look at our second question. Question B. We're looking at two particles. And the question is, these two particles have different numbers of what? Neutrons? Protons? Electrons? Okay, notice this is nitrogen, and this is the nitride anion. It's a negatively 3 charged anion that's derived from the nitrogen atom. So what do we know for certain about these particles? They have different what? So the first one, we're not really sure. We didn't tell you anything about the nuclear structure. So do they have different numbers of neutrons? We can't distinguish based upon the information that's given. Do they have different numbers of protons? They're both derived from the nitrogen atom, so they will have identical number, the same number of protons. So we know for sure that's not true. And as we said, we don't have enough information to say anything about the number of neutrons. What do we know that they have different numbers of? They're going to have different numbers of electrons. So this is the only statement that we know is true. This is an anion, and this is the atom from which it's derived. They're going to have different numbers of electrons. And we would expect that the nitride anion, since it's negatively 3 charged, it will have 3 more electrons in comparison to the nitrogen atom. So that's another question that you should be able to answer based upon the material that we went over today. What we're going to do in our next lecture, the final part of this lecture today, is discuss a little bit about the other number on the periodic table. And we really haven't spent any time on this. And if we look at our periodic representation of carbon, we've already talked about the symbol. Those are what we need to memorize. We talked about the atomic number as the number of protons. And the last part of this lecture, we're going to discuss more about this fractional number. This fractional number for carbon 12.011 is the average atomic mass. And what we're going to introduce in the next section of today's video lecture is we're going to introduce the atomic mass unit, and we're going to discuss where we get this number from, and we're actually going to go over a calculation involving how we can determine the average atomic mass, given some information about a particular atom in the elements. Thank you.